You've probably heard a lot about AI and machine learning over the last few months, and maybe you've been inspired by videos showing what's possible with AI and machine learning. But what is it really? Once you go beyond the hype and get down to writing code, what does AI really look like? Well, that's what we're going to go through in this video series, where we'll teach you what it's like to write code for machine learning and how it provides different, new, and exciting scenarios that will help you write applications that behave more like a human being, giving you artificial intelligence. I'm Lawrence, and I'm going to be your guide. You don't need to know a lot to get started, and we'll be using the Python language. Don't worry if you've never used it. It's super simple to understand, and you'll be up and running in no time. So let's start with a very simple example. Consider you're creating a game of rock, paper, scissors. When you play this with a human, it's very basic. Every child can learn it in just a few minutes. Now let's take a look at the most basic part of a game that the human brain is really good at, and that's recognizing what it's actually looking at. So consider these images. Most people can look at them and instantly recognize which ones are rock, which ones are paper, and which ones are scissors. But how would you program a computer to recognize them? Think about all of the diversity of hand type, skin color, and even people who do scissors like me with their thumb sticking out, and people who do scissors with their thumb in. If you've ever written any kind of code, you'll instantly realize that this is a really, really difficult task. It might take you thousands or tens of thousands of lines of code, and that's just to play rock, paper, or scissors. So what if there was a different way to teach a computer to recognize what it sees? What if you could have a computer learn in the same way that a human does? That's the core of machine learning and the path to artificial intelligence. So traditional programming looks like this. You have data, for example, a feed from the webcam, and you have rules that act on this data. These rules are expressed in a programming language and are the bulk of any code that you write. Ultimately, these rules will act on the data and give you an answer. Maybe it sees a rock, maybe it sees a paper, and maybe it sees scissors. But what if you turn this diagram around, and instead of you as the programmer figuring out the rules, you instead give it answers with the data and have the computer figure out what the rules are? That's machine learning. So now I can have lots of pictures of rocks and tell a computer that this is what a rock looks like, and this is what paper looks like, and this is what scissors looks like. And I can have a computer figure out the patterns that match them to each other. Then my computer will have learned to recognize a rock, paper, and scissors. That's the core of building something that uses machine learning. You get a set of data that has patterns inherent in it, and you have a computer learn what those patterns are. Before we write a neural network that learns something as complex as rock, paper, and scissors, let's use a much simpler example. Take a look at these numbers. There's a relationship between the x and y values. Can you see it? It's actually y equals 2x minus 1. So if you saw it, how did you get that? Maybe you noticed that the y value increases by 2, while the x value only increases by 1, so it was y equals 2x plus or minus something. And then you may have seen that when x was 0, y was minus 1, so you figured y equals 2x minus 1 would be a good guess, and then you took a look at the other numbers and saw that it worked. That's exactly the principle that all machine learning works on. So let's take a look. This is the entire code that you can use to create a machine-learned model that figures out what matches these numbers to each other. Don't worry if some of it doesn't look very familiar right now, you'll be able to pick that up in no time. This first line defines the model itself. A model is a trained neural network, and here we have the simplest possible neural network, which in this case is a single layer indicated by the keras.layers.dense code. And that layer has a single neuron in it, indicated by units equals 1. We also feed a single value into the neural network, which is the x value, and we'll have the neural network predict what the y would be for that x. So that's why we just say that the input shape is one value. When you compile the model, there are two functions, the loss and the optimizer. These are the key to machine learning. How machine learning works is that the model will make a guess about the relationship between the numbers. For example, it might guess that y equals 5x plus 5. And when training, it will then calculate how good or how bad that guess is using the loss function. And then it will use the optimizer function to generate another guess. The logic is that the combination of these two functions will slowly get us closer and closer to the correct formula. And in this case, it will go through that loop 500 times, making a guess, calculating how accurate that guess is, and then using the optimizer to enhance that guess, and so on. The data itself is set up as an array of x's and y's, and our process of matching them to each other is in the fit method of the model. We literally say, fit the x's to the y's, and try this 500 times. When it's done, we'll have a trained model. So now you can try to predict a y value for a given x. What do you think would happen if you tried this line of code, predict the y when x equals 10? You might think that the answer is 19, right? But it isn't. It's actually something like 18.9998. It's close to 19, but it's not quite there. Why do you think that would be? Well, the computer was trained to match only 6 pairs of numbers. It looks like a straight line relationship between them for those 6, but it may not be a straight line for values outside of those 6. There's a very high probability that it's a straight line, but we can't be certain. And this probability is built into the prediction, so it's telling us a value very close to 19 instead of exactly 19. Try the code out using the link in the description below this video to see it for yourself. This is something you'll see a lot more of in machine learning. In the next video in this series, we'll take what you've learned and apply that to a more interesting problem, computer vision, and seeing how you can teach a computer to see things using exactly the same methodology as you used here. We'll see you in that video, and don't forget to hit that subscribe button. Thank you. Hi everyone, and welcome to episode 2 of TensorFlow Zero to Hero. In the last episode, you learned about machine learning and how it works. You saw a simple example of matching numbers to each other and how, using Python code, a computer could learn, through trial and error, what the relationship between the numbers was. In this episode, you're going to take it a little further by teaching a computer how to see and recognize different objects. For example, look at these pictures. How many shoes do you see? You might say 2, right? But how do you know they are shoes? Imagine if somebody had never seen shoes before. How would you tell them that despite the great difference between the high heel and the sports shoe, they're still both shoes? Maybe they would think, if it's red, it's a shoe, because all they've seen are these two and they're both red. But of course, it's not that simple. But how do you know that these two are shoes? Because in your life, you've seen lots of shoes and you've learned to understand what makes a shoe a shoe. So it follows logically that if we show a computer lots of shoes, it will be able to recognize what a shoe is. And that's where the dataset called Fashion MNIST is useful. It has 70,000 images in 10 different categories. So there's 7,000 examples of each category, including shoes. Hopefully, seeing 7,000 shoes is enough for a computer to learn what a shoe looks like. The images in Fashion MNIST are only 28 by 28 pixels, so they're pretty small. And the less data used, the faster it is for a computer to process it. That being said, they still lead to recognizable items of clothing. In this case, you can still see that it's a shoe. In the next few minutes, I'll show you the code that will teach you how to train a computer to recognize items of clothing based on this training data. The type of code you write is almost identical to what you did in the last video. That's part of the power of TensorFlow that allows you to design neural networks for a variety of tasks with a consistent programming API. We'll start by loading the data. The Fashion MNIST dataset is built into TensorFlow, so it's easy to load it with code like this. The training images is a set of 60,000 images, like our ankle boot here. The other 10,000 are a test set that we can use to check to see how well our neural network performs. We'll see them later. The label is a number indicating the class of that type of clothing. So in this case, the number 9 indicates an ankle boot. Why do you think it would be a number and not just the text ankle boot? There's two main reasons. First, computers deal better with numbers. But perhaps more importantly, there's the issue of bias. If we label it as ankle boot, we're already showing a bias towards the English language. So by using a number, you can point to a text description in any language as shown here. Can you guess all the languages that we used here? When looking at a neural network design, it's always good to explore the input values and the output values first. Here we can see that our neural network is a little more complex than the one in the first episode. Our first layer has the input of shape 28 by 28, which if you remember was the size of our image. Our last layer is 10, which if you remember is the number of different items of clothing represented in our dataset. So our neural network will kind of act like a filter, which takes in a 28 by 28 set of pixels and outputs one of 10 values. So what about this number, 128? What does that do? Well, think of it like this. We're going to have 128 functions, each one of which has parameters inside of it. Let's call these f0 through f127. What we want is that when the pixels of the shoe get fed into them, one by one, that the combination of all of these functions will output the correct value, in this case 9. In order to do that, the computer will need to figure out the parameters inside of these functions to get that result. And it will then extend this to all of the other items of clothing in the dataset. The logic is, once it has done this, then it should be able to recognize items of clothing. So if you remember from the last video, there's the optimizer function and the loss function. The neural network will be initialized with random values. The loss function will then measure how good or how bad the results were, and then with the optimizer, it will generate new parameters for the functions to see if it can do better. You've probably also wondered about these, and they're called activation functions. The first one is on the layer of 128 functions, and it's called ReLU, or rectified linear unit. What it really does is as simple as returning a value if it's greater than 0. So if that function had 0 or less as output, it just gets filtered out. And softmax has the effect of picking the biggest number in a set. The output layer in this neural network has 10 items in it, representing the probability that we're looking at that specific item of clothing. So in this case, it has a high probability that it's item 9, which is our ankle boot. So instead of searching through to find the largest, what softmax does is it sets it to 1 and the rest to 0, so all we have to do is find the 1. Training is then very simple. We fit the training images to the training labels. This time we'll try it for just 5 epochs. Remember earlier we had 10,000 images and labels that we didn't train with? These are images that the model hasn't previously seen, so we can use them to test how well our model performs. We can do that test by passing them to the evaluate method like this. And then finally, we can get predictions back for new images by calling model.predict like this. And that's all it takes to teach a computer how to see and recognize images. You can try this out for yourself in the notebook that I've linked in the description below. Having gone through this, you've probably seen one drawback, and that's the fact that the images are always 28 by 28 grayscale with the item of clothing centered. So what if it's just a normal photograph and we want to recognize its contents, and you don't have the luxury of it being the only thing in the picture as well as being centered? That's where the process of spotting features becomes useful, and the tool of convolutional neural networks is your friend. You'll learn all about that in the next video, so don't forget to hit that subscribe button, and I'll see you there. Hi, and welcome to episode 3 of Zero to Hero with Tensorflow. In the previous episode, you saw how to do basic computer vision using a deep neural network that matched the pixels of an image to a label. So an image like this was matched to a numeric label that represented it like this. But there was a limitation to that. The image you were looking at had to have the subject centered in it, and it had to be the only thing in the image. So the code you wrote would work for that shoe. But what about these? It wouldn't be able to identify all of them because it's not trained to do so. For that, we have to use something called a convolutional neural network, which works a little differently than what you've just seen. The idea behind a convolutional neural network is that you filter the images before training the deep neural network. After filtering the images, features within the images could then come to the forefront, and you would then spot those features to identify something. A filter is simply a set of multipliers. So for example, in this case, if you're looking at a particular pixel that has the value 192, and the filter is the values in the red box, then you multiply 192 by 4.5 and each of its neighbors by the respective filter value. So its neighbor above and to the left is 0, so you multiply that by -1. Its upper neighbor is 64, so you multiply that by 0, and so on. Sum up the result and you get the new value for the pixel. Now this might seem a little odd, but check out the results for some filters, like this one, that when multiplied over the contents of the image, it removes almost everything except the vertical lines. And this one, that removes almost everything except the horizontal lines. This can then be combined with something called pooling, which groups up the pixels in the image and filters them down to a subset. So for example, max pooling 2x2 will group the image into sets of 2x2 pixels and simply pick the largest. The image will be reduced to 1/4 of its original size, but the features can still be maintained. So the previous image, after being filtered and then max pooled, could look like this. The image on the right is 1/4 the size of the one on the left, but the vertical line features were maintained, and indeed they were enhanced. So where did these filters come from? And that's the magic of a convolutional neural network. They're actually learned. They're just parameters like those in the neurons of a neural network that we saw in the last video. So as our image is fed into the convolutional layer, a number of randomly initialized filters will pass over the image. The results of these are fed into the next layer, and matching is performed by the neural network. And over time, the filters that give us the image outputs that give the best matches will be learned, and the process is called feature extraction. Here's an example of how a convolutional filter layer can help a computer visualize things. You can see across the top row here that you actually have a shoe, but it has been filtered down to the sole and the silhouette of a shoe by filters that learned what a shoe looks like. You'll run this code for yourself in just a few minutes. Now let's take a look at the code to build a convolutional neural network like this. So this code is very similar to what you used earlier, where you have a flattened input that's fed into a dense layer that in turn is fed into the final dense layer that is our output. The only difference here is that I haven't specified the input shape. That's because I'll put a convolutional layer on top of it like this. This layer takes the input, so we specify the input shape. And we're telling it to generate 64 filters with this parameter. That is, it will generate 64 filters and multiply each of them across the image. Then, each epoch, it will figure out which filters gave the best signals to help match the images to their labels in much the same way it learned which parameters worked best in the dense layer. The max pooling to compress the image and enhance the features looks like this. And we can stack convolutional layers on top of each other to really break down the image and try to learn from very abstract features like this. With this methodology, your network starts to learn based on the features of the image instead of just the raw patterns of pixels. 2 sleeves, it's a shirt. 2 short sleeves, it's a t-shirt. Sole and laces, it's a shoe, that type of thing. Now we're still looking at just the simple images of fashion at the moment, but the principles will extend into more complex images, and you'll see that in the next video. But before going there, try out the notebook to see convolutions for yourself. I've made a link to it in the description below. And before we get to the next video, don't forget to hit that subscribe button. Thank you. Hi everybody, and welcome to the fourth and final video in this series of Zero to Hero with Tensorflow. I'm Lawrence, and today we're going to look back at the very first problem that we spoke about, and then we'll see how we can build a machine-learned model to solve it. Remember this, all the way back in episode 1, where we showed a scenario of rock, paper, and scissors and discussed how difficult it might be to create an application that recognizes hands of different shapes, sizes, ethnicities, decorations, and more. We discussed how difficult it would be to write code to detect and classify these, even for something as simple as a rock, paper, or scissors. But since then, you've looked into machine learning and you've seen how to build neural networks, first to detect patterns in raw pixels to classify them, and then to detect features using convolutions to have a convolutional neural network trained to spot the particular features that make up an item, like the soles of a shoe. Let's put all that together, and in this video, we'll see how to create a neural network that is trained on data of rock, paper, and scissors to detect and spot them. We'll start with the data. There's a data set here that has several hundred images of rock, paper, and scissors poses. We'll train a neural network with this data. So first of all, we have to download the zip files containing the data. The code to do that is here. One file has the training set, the other has a testing and validation set. In Python, you can unzip a file with the zip file library, and we unzip them to a temp directory like this. This creates folders with subfolders of each of our categories. When training in TensorFlow using an image data generator, it will automatically label the images based on the name of their parent directory, so we don't need to create labels for the images. It's a really nice shortcut. So I'll achieve that with this code. This creates an image data generator that generates images for the training from the directory that they were downloaded to. We can then set up something called a training generator, which, as its name suggests, creates training data from that. We can do exactly the same for the test set with this code. Later, when you see the model.fit, you'll see that we pass these in as the training and validation parameters. Now let's look at our neural network definition. This is very like what you saw in the last video, just with more layers. One reason is that the images are more complicated than the grayscale clothing you saw previously, and another is that they're bigger. You can see that our input is now 150 by 150. Our images are certainly bigger than they were before. And our output is a layer of 3 neurons. Well, why would that be? Because there are 3 classes, rock, paper, and scissors. Between these, the code is very similar to what you saw previously, just more of it. So we have 4 layers of convolutions, each with max pooling, before feeding into a dense layer. The dropout is a little trick to improve the efficiency of a neural network by throwing away some of the neurons. We'll compile the neural network as before with this code, and then we can fit the data with the model.fit call. Note that we don't have labels. That's because we're using the generator. It's inferring the labels from the parent directories of both the training and the validation datasets. When you run this, you'll probably get accuracy of about 100% on the training data quite quickly, with the validation data getting to about 87% accuracy. This is something called overfitting, which happens when the model gets really good at spotting what it has seen before, but it's not so great at generalizing. Think about it this way. So for example, if all your life the only shoes you had ever seen were hiking boots, you probably wouldn't recognize high heels as shoes. You would be overfitting yourself. There are a number of methods to avoid this, and one of them is called image augmentation. And I've put the code for this into the notebook for you to try yourself to see how it helps avoid overfitting. Once your model is trained, you can then call model.predict to see how well it spots rock, paper, or scissors. This code will take an image, reformat it to 150 by 150, which the model is trained for, and it will then return a prediction. And here's a few examples that I ran so that you can see that it's actually predicting quite well. But the best thing to do is to try it for yourself. I've put a link to the notebook in the description below, and you can use this code to train a neural network to recognize rock, paper, and scissors images. That's it for this short series of videos. I hope it was useful for you to see the new programming paradigm that is machine learning, and through these examples of computer vision, how you can get yourself on the path to become an artificial intelligence engineer. If you have any questions, please leave them in the comments below, and don't forget to subscribe for more great content. Thank you.